Hey, it's Tony from Adafruit, and in this video we're going to look at how to use capacitive touch sensing with CircuitPython and even MicroPython this could work with. And capacitive touch is something you might have seen on a board like this. This is Circuit Playground, so it's our all-in-one electronics learning board. And the cool thing is all of the pads on the outside here have capacitive touch sensing built in where you can touch them with your finger and that changes the capacitance that the board detects, and it can tell when you touch it and when you don't touch it. You might remember the old lamps from like the 80s that you would touch the base of the lamp and it would turn on. It could detect when someone touched it, and that's again using capacitive sensing. So it can tell when the capacitance of something changes because a big human that's a big kind of, I don't know, just mostly water, so big sack of water basically touches something, changes the capacitance, and that can be detected, and then in your code you can do something like play music, maybe play a sound effect, something fun and interesting. So we'll look at how to use this in MicroPython and CircuitPython specifically, and I'm going to show you how to use it with something that's not out yet. So it's with our Express boards, so the Metro Express, the Feather M0 Express, or the Circuit Playground Express boards. I'm not sure that's the final name, but basically these are boards that use the SAMD21 microprocessor. They can run MicroPython or CircuitPython, and then they also have a little flash chip so that you can store your Python code on that flash memory instead of the internal memory. And the nice thing is that gives us more space for the CircuitPython firmware so we can add extra features. So long story short, the cool thing is for those Express boards, they have built-in support for capacitive touch that's a part of that SAMD21 microprocessor. Now, unfortunately, you can't use it with, well, I'll show you in a moment here, the non-Express boards. So the boards like that you can buy right now, the Feather M0 Basic or the Adalogger, those boards don't have that little flash chip. So you can only put a MicroPython firmware on there that's as big as the internal flash file system or the internal flash of the chip. So it's not big enough basically to add this touch support. But what I was thinking we'll do in this video stream is I'll actually port our MPR121 capacitive touch sensing breakout. It's a little breakout board right here. So this is actually this is the Feather M0 Adalogger on the bottom here. So it's our Feather M0 board. But again, this is the board you can buy right now that does not have that extra flash memory chip on it. And then on the top here is the MPR121 capacitive touch sensing breakout. So this is kind of nice in that you can connect a little breakout board like this to any Feather M0. And then I'm going to write the code in this video stream to talk to that MPR121 capacitive touch sensing chip, and it will do the same functionality that's built into a chip like this. So this is, or a board like this rather, I can't really move it out of the way, but this is the Circuit Playground Express. So this is that same SAMD21 microprocessor as in, the Feather M0 boards, but it has this extra little flash memory chip so we can make the MicroPython firmware or the CircuitPython firmware on here a little more full-featured, and it can add stuff like that capacitive touch sensing support. So bottom line is it'll be really neat when these boards are out. You'll be able to do capacitive touch sensing, and I'll show you real quickly a demo of it. Very easy. It'll be built into the firmware. But if you've got the boards today, like the Feather M0, the Adalogger, or the basic one back here, then we'll look at how to port over the driver, and I'll actually do that now. I haven't really ported this driver yet, so this will be kind of two things in this stream. It'll be a good introduction to how to write a driver for CircuitPython, and then at the end of this, hopefully I'll have a basic working driver that you'll be able to use. And when this goes up on YouTube, I'll put links in the description below to the code and things that I create from this video stream. And who knows, it might run into issues, might completely fail, so this is a little bit more of on-the-fly kind of thing. So okay, let's jump into the main view with everything. So here is the hardware. And again, like I said, I'll start out, I'm just going to do a quick demo of, this is the Circuit Playground Express. You can't buy this yet, but probably in the next month or so, you'll be able to buy this board. And it's the SAMD21 microprocessor with a little flash memory chip so that you can store your Python code on there. And then that lets us add extra cool features like this capacitive touch support. And sorry, there's a little bit of glare. The cable is holding it at just the right angle to get the exact amount of glare to make the board unreadable. But that's okay because I'm just going to be touching the pads on the outside. So I'll show you how to use this. I've connected the board, and I'm just going to open up the REPL, so the serial REPL, dev tty USB modem 115200 baud. Okay, so I'm at the REPL, And for these express boards that have the built-in capacitive touch support, it's as easy as using in the native I/O module. There's a touch-in class. So first I need to import the board module, because this gives me all of the pins that are on the board. Like all these outer pins are labeled, there's A5, A6, and those pins, or those kind of pads, are what I can use for my touch sensing. But I need to be able to see which those are, so this lists all the boards, all the pins that are on the board. And you might not be able to tell, maybe if I zoom in a little bit, let's go telephoto. So you can see, like on the outside here, well, maybe if I hold it up here, here's pin A10, A11, and you can see on the screen here, we have board pins defined like A11, A10 right here. So that's how you reference those pins. Let me zoom back out a little bit. Okay, so board module gives me those, and then the native I/O module is what I need to import to get that touch input class. And then to make a touch input on, let's say A10, this one on the bottom right here where my thumb is touching, let's make a touch object, and this is going to be a native IO.touchIn, and I need to tell it which pin that I want to use. So this is A10, and oops, it's not native, it's native IO. So let's get that correct. There we go. Okay, and then to read the value of this, because with capacitive touch, you're basically just looking to see, is something touching it or not touching it? Now there's a lot more to it. I think there's all kinds of tuning and things you can do. We don't expose that in CircuitPython, but you can basically say touch.value, and that's going to give you a Boolean, a true false. So it's false because nothing's touching it, but if I put my finger on there, let's see what happens. So hey, it's true. So it detects, I'm touching it, take my finger away, gives false, and then I touch it, and I run this again, and I get true. So that's pretty cool. And you can imagine I could put this in a loop. And so, well, I don't know, let's do that. So let's say while true, actually first, let's import the time module, and then we'll say while true, so just infinite loop. If touch.value, we'll say print touched. And then let's just have this sleep for, let's say, a quarter second. So every quarter second, it's going to look and see if something's touching this. And then, okay, so now my loop is running and nothing's touching it. And then if I touch this, hey, cool, it detects it, take my finger away, and then I touch this again. And the cool thing with this capacitive sensing, I can put something conductive. I can connect a wire to this A10 pad. Like this is a little alligator wire. So I'm going to do that. I'll connect one end to the board, so I've got that connected. And actually interesting, it's constantly detecting this as touched, and I think the thing is, when I initialized this touch input, it probably initialized itself based on the capacitance that it detected. Now that I've connected this thing, I've probably messed that all up. So let's Control C out of this loop, and let's recreate our touch object again, and let's see. I'm kind of curious. I'm not sure if this will work, but let's see if this works. So touch.value, okay, so now it's false, and I'll zoom out and let's go wide on this. So you can kind of see here is the other end of this alligator clip. So I'm not touching it, touch.value is false. If I touch this, so I'm touching this with my fingers, let's see. So hey, it's true. So it can pick up and detect that I've touched something there. And of course, a really fun demo with this is you can connect the other end of this alligator clip to like a piece of fruit, like a banana or an apple, and then you can actually detect, when that fruit is touched, and you can make the classic kind of fruit orchestra where you touch a piece of fruit and it plays a sound or something like that. So anyways, that's how easy capacitive touch sensing will be with these don't ask, they're not out yet express boards. So in the future, it'll be pretty simple when you get one of these express boards. You load up the CircuitPython firmware, and it'll likely have this touch input enabled by default. Although who knows? I mean, this is an optional part of the firmware, so it kind of comes down to if we have space available in the firmware to include it. But we're hoping to include as much as we can in those boards that have the flash memory, the little SPI flash. Okay, so now for the second part of this video, I'm going to go in and like I mentioned, because unfortunately I was hoping to show a demo of capacitive touch that anyone could use right now. And so, for example, you can't get this Circuit Playground board yet that has that SAMD21 processor, but you can get one of these. This is the Feather M0. This is the Adalogger version, which has a little SD card, but you can get the Feather M0 Basic. Any of the Feather M0 boards have that SAMD21 microprocessor. And again, it's the same microprocessor as on the Feather, the Circuit Playground right here, but and so it has that exact same it's called Q-Touch, is the capacitive touch sensing hardware that's built into the little microprocessor, the SAMD21. So that same hardware is here, but the problem is adding that support to CircuitPython requires more space than we can fit into the processor's little flash file system that we have for the firmware. So basically there's not enough room on the chip, the memory that it has available, to add the code that can talk to that flash or that Q-Touch peripheral. And actually, maybe in the future that might change. I think Lady Ada did some cool videos where she was reverse engineering how that Q-Touch works, because right now we have to include this really large binary blob to get that support, and at the end of the day it's just tweaking some little registers, so that shouldn't require like 8 kilobytes of included source files. So maybe this will work in the future without all this giant extra support, and maybe you'll be able to use that touch input natively on these SAMD21 boards. But for now, a really easy way and a surefire way to do capacitive sensing with any board that can talk to I2C. So this would also work with like the ESP8266, which has no capacitive touch sensing built into it. You can add an extra board like this top board right here that I mentioned, the MPR121. Let me zoom in a little bit here, and we'll move the circuit playground out of the way. Oops, let me open up a new window here. And okay, so I'll move that out of the way, and we'll just kind of see. Oops, we'll zoom out a teeny bit there. I'm going to plug in the M0 board right here. So okay, and like I mentioned, I'll show you real quick too, and I'll put a link to this product page when this video is up on YouTube. So look in the description below, you can see a link to this board. This is the board that I have right here. This is the MPR121 capacitive touch sensing board. It's really nice and simple. Basically, it has these 11 inputs at the top, and these are the capacitive touch sensing inputs. And so you can connect a wire to them, and then you can connect like, an alligator clip like we saw before. You can use one of those. You can just touch them with your finger directly if you want for testing. It's pretty straightforward to hook this up however you need. And then it just needs an I2C connection to your hardware. So there's an SCL and an SDA line. That's basically your I2C clock and your I2C data line. And then you also need a voltage input like 3.3 to 5 volts, and then a ground connection. So that's how I have this connected right now. So and eventually I'll write up a proper guide once I finish this library. But for now, hey, like I said, this will be both a demo of how to create a library and how to use this MPR121 with CircuitPython. But the way I've wired this up, basically I've connected this white wire is going to the V-in, the voltage input of the MPR121. That's connected to the 3.3 volt output of the feather board. And then the black wire, this is ground, so it's connected to the ground, the GND pin on the MPR121. That's connected to ground on the feather M0. And then the yellow wire is connected to the the SDA data line, and that's connected to the SDA output on the feather M0. And then the orange wire, this is connected to the SCL line on the MPR121, and that's connected to SCL on the feather M0. So it's just a standard I2C connection, nothing fancy or crazy here, which is nice. Okay, so now for this module, I already have some Python code that talks to it. I'll put a link in the description to this code, but this is for the Raspberry Pi. This is the Adafruit Python MPR121 library. So you can't use this directly, but I'm going to use this as a base for writing my CircuitPython driver, because the code is going to be pretty similar, and hopefully maybe a year from now it'll actually be the same, because we'd like to move all of our Raspberry Pi code to use the same code as our CircuitPython and MicroPython drivers. It'd be really cool if there's one Python driver that just works on everything, and there's not really much stopping us from doing that other than writing a bunch of the code and the shims and things to make it work. Anyways, though, this is kind of nice, and this will give me a good base to get started with. And really the way that you talk to this chip, and when you're doing any driver porting, you're going to want to look at the data sheet. So let's look at MPR121 data sheet for sure. Let's just open that up. And so let's see, we'll go to the Adafruit one. It looks like the top hit is for SparkFun, which maybe we need a little bit better SEO. Oh, this is for the guide itself. Let's see if, well, okay, hey, SparkFun wins out. Looks like they've got the datasheet link at the top. So we'll go to the datasheet here. And again, if you're porting a driver over, this is not for beginners. Like, you're going to need to know how devices work somewhat at a low level. So you're going to need to be comfortable with reading the data sheet. But this is basically going to tell you about all of the physical connections on the chip, like how it needs to be wired, if there's other components and things that need to be connected to it, which you usually don't need to worry about when you're using a breakout board, because the breakout board is designed to have all those components and things connected to it. But this will also tell you about the protocol for talking to this chip. And so if I scroll down, I'm sure it has like a register map on here. So you can see here's the register map. So for most I2C devices, you just have a big list of registers. Each register has an address, and then each register is typically a fixed size, like 8 bits or 16 bits. You know, sometimes 2 registers next to each other make a larger 16-bit register. And those give you your values. So it depends on this hardware. Like it has a register for each of these capacitive touch sensing inputs at the top. There's a register that's going to have some data inside of there, and I need to know how to interpret that data to figure out, you know, did it detect the touch or not? And so again, luckily I've already done most of that with this Raspberry Pi Python driver, so I can just go through and see in this driver what it does. It really just does a lot of these write commands where it's like writing to a register. So this write 8 command writes to the soft reset register, this 063 value, and then it can also read values. So I have later on in this code, there's like this read U8 function, which would, in this case, read this config register and check that it gets a certain value back for this. So let's go in and let's see if I can quickly write a little port of this driver code to CircuitPython. And like I said, I haven't done this yet, so this might be a crash and burn failure. I did some basic testing and it looks like it should be possible. So famous last words, you might see me flailing for you know, maybe 30 minutes or so. And who knows, maybe there'll be a part 2 to this video where I come back and figure out how to make this thing work. So okay, let's first just connect to the serial REPL on this board. So again, you know, I connected my Feather M0. By the way, these are running the latest versions of CircuitPython, the 0.9.1 release. Always a good idea to update to the latest version. I just pressed enter to stop the auto reset logic because I just want to play around and first just detect that my breakout board is being detected by the I2C bus. So I'm going to import the board and the native I/O modules, and I'm going to set up the I2C bus. So this equals native IO.I2C, and I need to tell it the clock and the data lines that I'm using. I've gone through this a lot before. This is just your typical I2C bus initialization. And then I should be able to call the scan command if I remember correctly. So yeah, you can call I2C.scan, and this is going to look to see what devices are connected, or like what devices are detected on this I2C bus. So it detected a device with the decimal value 90, and I can convert that to hex if I remember correctly. I'm trying to remember my Python hex conversion. I can't remember how to do that conversion, but what I can do is if I go to the data sheet, or even if I just look in my my driver code right here. So in my driver code, the address that I assume is this MPR I2C adder default, which is at the top right here, this value right here, so OX5A. So if I look at the value OX5A, converted to decimal, that's 90. So this is good. This is telling me that when I call I2C.scan, it found a device with address 90 that responds, that's connected and says, yeah, I can send and receive data. And that matches the address that I expect for the MPR121 chip, that OX5A value right there. So that's good. It just tells me I've got the chip connected and physically, you know, I'm good to go to talk to this thing. Now I'm going to look at my driver, and basically what I do in my driver is I set up this I2C device using the address that was passed in. This code above here just tries to make the Raspberry Pi code work either with the Raspberry Pi or other I2C boards and things. So it's not necessary for CircuitPython. But ultimately I see that I'm calling this reset function, and then in this reset function there's a bunch of different calls to modify, you know, like these calls right here where I'm setting up all the registers of this device. And so that's what I want to kind of start with on my port of this code. So let's just start out by editing. I'm just going to make like a single Python file that, you know, I'm not going to make this a proper library yet. I'm just going to maybe make this like a one 1.py file that has all of the code inside of it, and then I'll break that out into a separate file, just because it's a little bit easier, I think, to work on things kind of in isolation, and then slowly change things. If I try to make this a proper library, like or I have a module with an init.py, there's just a lot of overhead. Like I just want to get the basics working first, and then I can make this into like a more modular kind of thing. So okay, so I'm just going to redo the code that I just had before. So we'll say import board, and actually let's save this as let's say MPR121.py. We'll call this. Okay, and import native IO. So again, I just want to be able to set up that I2C bus instance. And then here, this is kind of your typical Python convention for having code that only runs when it's when the module itself is run, and not when you import the module. So here's where, and actually this is maybe where I should put this code, because I'm thinking up here is where my driver code goes, and then down here is where like example using driver code will go. So this code is eventually what I'm going to break out into a separate example.py file. But for now, I'm going to put my driver up here, and I'll have my example code down here. But anyways, let's put in this I2C. Let's make that I2C bus, native.io.I2C, say board.scl, board.sca. Okay, so now at this point, let's make an MPR 121 class. And let's give it an initializer. And this is going to need to take in an instance of the I2C bus for sure. And so I'm going to take that in, and let's save that as I2C. And so now in my example code, let's make an MPR121 object, and I'll give it that I2C device right here. And in my example code, let's just have it print out done, just so that I know that it ran and that it got that far. Okay, so let's just save this. I'm going to quit. And I'm going to set my ampy port variable to tty.usb modem. This is just so that I can use ampy commands, and I don't need to specify the port variable all the time. So if I do ampy run this MPR121.py, it ran, it created my object basically. So this example code right here ran, and then you can see it printed out done, and then I get that output here. So I know all my code ran. I didn't get an error message, which is good. Okay, so in my initializer now, let's have it check that device is available on the bus. And there's actually a cleaner way to deal with I2C devices, because if I look at my Python code, it's using this I2C library that I created, where I create an instance of this I2C device class, and I pass it the address. And then it will remember, that address is this value up here, that OX5A. It will remember that, so every time I talk to my device, it knows the address of it. Whereas right now in the CircuitPython code, if you're dealing with the I2C bus at a low level, you always have to specify the address of the device. So just as an example, I'll show you maybe how to do this without an I2C device wrapper class, and then I'll show you this nice little wrapper class that we have. But anyways, so I'm going to start porting over this reset function right here. So the very first thing it does is it writes a byte to this soft reset register. So it writes the value OX63. And if I looked at the data sheet, I'm sure it would tell me what that OX63 means. But just for the interest of time, I'm not going to go through that right now. But again, that's why you're going to want to look at the data sheet, because you'll need to figure out what these magic values are and what they mean. But here's how you write a byte to a register on a device. So with this I2C module, so let's see, we'll do this port kind of almost as is, like a one-to-one with the Raspberry Pi code. So let's just have it call that reset function on our device. So in that reset function, so first of all, write to the reset register. And so what I want to do is I want to basically take this call and port it over to CircuitPython. Now, in the Raspberry Pi code, I prefix everything with this I2C retry. For some reason, I remember when I created this module on the Raspberry Pi, it was really flaky and it didn't work very well, and so I just had it retry. And I think that's because there were some bugs in the Raspberry Pi's I2C logic, because this hardware kind of requires this repeated start condition mode. So it's a little bit weird. I can't remember exactly why I ran into this problem, but doing this retry fixed it. So I'm going to try this without doing retries on the CircuitPython code, and we'll see. Hopefully it works, because I'm assuming this was just a problem specific to the Raspberry Pi. But anyway, so I need to write the value 63 to this register on that device. And so I'm actually going to copy, let's grab all these register defines up at the top right here and throw these into my file, because these are probably going to be super useful and necessary for me. Okay, so to write to that device with the CircuitPython code, I need to call I2C, or well actually self.I2C. So that's the I2C bus instance that I've saved on my device right here. And there's a write to function. And then I need to just pass this a list of bytes to write. And this is just going to write those bytes out to the I2C bus. So this doesn't have a concept of what device it should talk to. I actually need to tell it which device I'm going to talk to, which I'm going to talk to this I2C, basically this little device that's connected to my I2C bus. So I can do that by just passing a list of bytes to my device right here. So if I pass in a bytes object, and then the bytes object, you have to pass it a list or an iterable. And so now I can just pass it some bytes, and it's going to blast these bytes out. So if I pass in my address of my device, and then if I pass in the register to my device that I want to write to, so that's my soft reset register. And then if I pass in the value I want to write, this should write all three of these bytes out to the I2C address, or to the I2C bus. So my device should see that, and it should reset itself. Now I say all this should work, but let's run it and let's see what happens, because this is a little bit different than how I did it before. So let's see if we get an error or anything. Okay, so we got something wrong. So can't convert bytes to integer. Okay, so this is interesting. So something is wrong at line 49. So it can't convert this bytes to, I'm sorry. The write to function actually takes in the address as the first parameter. That's right, sorry, I was getting a little bit confused there. So this write to function takes one parameter, which is the address of the device you want to talk to. The second parameter then is the list of bytes. And then for this list of bytes, I need to pass it, here's the register I want to talk to, and then here's the value I want to write to that register. So I had a little mixed up there, and I was thinking more of like a SPI device. With SPI devices, they usually don't have a concept of registers built into the SPI API. You're just reading and writing raw lists of data, whereas with I2C, there's typically always a concept of a device, at least by address that you're talking to. Okay, so let's try this again. And okay, there we go, we get her done. We got the done result. And so that's at least telling me that I didn't get an error. As far as I know, this worked and the chip reset itself. But let's keep going and we'll see. So this is an example of maybe a low-level write where I can specify the address of the device. But there is a nice little wrapper that we have in the Adafruit code. So we have a concept of a bus device object. And so a bus device object, and I've talked about this before, so we have this bus device library, and this basically gives us a little wrapper around I2C and SPI devices. So for I2C devices, I can create this I2C bus device, I tell it the address, it will remember that address, and then it gives me a write function that will automatically add that address, so I don't have to always remember to use that address. And I'll show you how I use this. So the first thing I've done is actually on my CircuitPython board, I've copied over the bus device module because basically I need to use this module, so I need to have the code on here. I've shown how to do this. Anytime you use a library, you have to copy that library over to your board. So what I did was I went to the bus device library right here on GitHub in the releases page. We put all of our releases. You grab the zip file, unzip the file, and then drag that folder onto your board so that you can see on my board I have the Adafruit bus device module. And there's also this register module. We'll come back to this. I don't know if I'm going to have time to use this module, but basically this register module is what you use. You can abstract away the registers to have kind of higher level objects that are easier to deal with. But I don't know if I'm going to have time yet to implement that kind of style. But that maybe in a future video I'll come back and look at how it could simplify the driver code. Anyways, long story short, let's import the Adafruit bus device .I2C device as I2C device. So this lets me use the I2C device class. And so now, instead of saving the raw I2C bus that the caller passed into me, I'm going to create an instance of the I2C device.I2C device object. And this is, again, coming from this bus device module. So inside of here, it has this I2C device class. And then it needs to know the I2C bus and then the address of the device that I want to talk to. So I'll pass in the I2C bus. And then right here, I'll take this as another parameter, but I'll give it a default value that defaults to the default I2C address. So we'll give it that value. And then right here, I'll tell it the address of the device. So okay, so now I have an I2C device object instead of the raw I2C bus. And the nice thing is this I2C address, or this I2C device, you need to use it like a context manager. So you call this with self.I2C. That basically will do, there's this locking internally that it needs to do before it can talk to the I2C device. But then at this point, now I don't need to specify this address anymore. So it has a write to function, but basically it doesn't require sending that address. So it just simplifies my code. I don't need to have all this low level, always remembering to send my address. This I2C device class remembers that address and it's going to send it. So let's save this, and hopefully if I got everything right, this will run. And okay, yeah, so this ran again. I got done. I didn't get an error message. So as far as I know, everything is working. So let's charge on and let's see if we can finish porting this over. So the rest of this reset code, let's grab, maybe I'll grab up to here and we'll look at porting this code over. Okay, so there's a small sleep that we put in here, so I'm going to need to import the time module. So we'll add that to the top. And I think it's just because when you reset the device, there's a very small period of time where it's not going to be responding. And this CircuitPython code is pretty slow, so I bet that I don't even really need this. But it can't hurt, so I'm going to do that. Okay, I'm going to fix the indenting. And now, so I set the electrode configuration to the default value. So again, this is a write to this MPR121 ECR register. So I want to write this value. So it's going to be really similar to the code above here. So I'm just going to replace this code with that and just fix up all of my parentheses and things. So okay, so this should write that value. Now the next thing is interesting. This is going to do a read. So it's going to read from the MPR Config Register. And this is a little bit different. So with this I2C device module, when you want to read, you actually have to do two commands. I need to write to the I2C device and say, hey, here's the register I want to read. And then I need to do an I2C read command that reads the number of bytes back that I care about. So I'll show you how to do this translation, because basically what this little line or 3 lines right here is doing is it's reading the config register and it's checking that it gets the value 0x24. So that's just checking to see that the device was reset and is back in a known good state. So to make this work, I'm going to do a write to my device, and I'm going to write the bytes of this config register, and then I'm going to do a read. But there's actually something wrong that I'm not doing correctly right now, and I'll show you what that is in a second. But I'm going to show the mistake first, then I'll show you the right way to do this. So now I'm going to do, there's a read from into, if I remember correctly, or I think it's either read from or read into. Yeah, so there's this read from into function, which basically will just read a number of bytes from my device. And so I need to actually have a result kind of buffer here. So we'll say this is a byte array of size 1. So this is going to store the result of this read command. And so this read command, then it's going to read the number of bytes specified in this object. So it's going to read 1 byte because this is a byte array of size 1. So this will basically read 1 byte from the I2C bus. So I'm going to do that. And so now my results is an array, and the very first item in that array will hopefully have the value 0x24. And if it doesn't, let's have it throw an error. So we'll say throw runtime error, or sorry, raise runtime error. We'll say failed to find MPR121 in expected config state. Something like that. We'll have it do that. So, okay, and then this line I don't need because that was the line that we're trying to convert. So what I've done here is I've turned, what was this read8 command on the Raspberry Pi, which kind of wraps up this logic. I have to do this as two lower level. I do a write, where I write the register that I want to read to the bus, and then I read my a number of bytes back, and I'm going to read 1 byte back, a byte array of size 1 back. I'm going to check that I get the value 0x24 from here. So let's save this, and let's see what happens when I run this. So, I get an error message, runtime error, failed to find MPR in expected config state. So the problem here is that each of these I2C commands is a separate I2C transaction, when in reality this read is actually a write and a read. And what happens here is when this write call runs, it ends with an I2C stop bit that says this I2C command is done. There's nothing extra that follows this, which is usually what you want when you're like writing out a new register value, like above here. But in this case, I'm writing out the register, but then I want to continue and do a read after that. And so what you need to do is specify this stop equals false. So this is a little optional keyword parameter that says, don't send that I2C stop bit at the end of this write command, which is going to tell the chip that I'm not done yet. I've written out some data, but now I'm going to do a read, and I'm going to expect you to send me some data back. So let's save this, and fingers crossed this will work. I've not done this way, but okay, hey, look, that worked. So I got to the done. So I know for sure then I got a result back, and the value in that result equals this 0x24 value that my code expected. So this is good. It looks like my MPR121 reset itself, and it's back in it's in kind of its default config state. So let's continue on here, and let's keep porting this code over. So, okay, the next thing is we call this set thresholds function. So let's add this to our library. So we'll say set thresholds, and then I need to add this function myself. So we'll say set thresholds, and this is gonna be a port of this function right here. Well, actually here, let's just copy the whole function over as we go with this. So, okay, I'm gonna remove the comments just because they take a bunch of memory, but when I actually port this for real, or when I clean this up and publish this, I'll probably add those back in, because when you generate an MPY version of this file, it's not gonna have those comments, and it's gonna be a lot more efficient. Okay, so I'm going to comment out these asserts. Well, what the heck, let's leave them in. It can't hurt to have these asserts in here. So again, these could be optional though. If I want to save memory, I might want to pull these out. But anyways, okay, so this is going to go through, and it's going to write for each of these addresses some values in here. So it's going to write, basically it looks like it goes through and it sets each of these registers. It computes each register based on a starting register, and then it adds an offset to it, and it writes this value to it, this touch and this release value to it. So, okay, so this shouldn't be too hard to port. It's gonna look a little bit like this, basically. So I first wanna get my context manager in here, and then I'm gonna put this loop inside of that context manager, and then let's grab this out of here. And okay, so I'm gonna wanna write to this location, and I'm going to want to write my touch value. So let's pass that in. And then I'm going to want to do the same thing, but for the other register that's below it right here. So I'm going to want to write this value, or this address rather. So I'm going to compute the address, and then the release value I want to write inside of there. So I do that. And okay, so let's do that. And then let's run our code just to make sure that nothing is exploding. And okay, I messed up some indentation here. So line 66, the indentation, What is this thing mad about? Let's see. So it doesn't like my indents here. I think this is just, it's mad about some of my spacing. 1, 2. Oh yeah, it looks, I've got tabs in here. Tabs versus spaces. This is every Python programmer's nightmare. I don't know how I got these tabs. I think GitHub. I'm going to blame GitHub on this one. It adds tabs and spaces. All right, let's manually fix the spacing right here. So, okay, let's put this in here. There we go. Let's fix that. And then fix that. And then fix that. Okay, so I think I've got my spaces correct. Oh, maybe I had that right. Okay. Uh-oh, it's not doing anything. That's not a good sign. Let's see. I'm gonna Control-C out of this. Let's see if, interesting. It might be getting stuck. Oh, so I think what's happening here, this is interesting. So I'm taking this lock with this with command, but I'm trying to take the lock again right here. And I guess our lock logic is not smart enough right now to realize that this lock has already been taken. So I actually just deadlocked it when I did that. Interesting. I didn't realize that that's possible. So, you know, what was happening there is internally this with command calls this try lock, which has to take a lock on a device. And if something already has that lock, it will wait until it releases that lock. But the thing that has that lock is the function that called this function. So it's waiting for, both functions are waiting on each other to finish, and you get deadlock in that case. So it's not ideal. It's nice. It would be nice if this was able to detect that the lock was already taken in this case, in which case, you know, I'm going to come back and fix this. But basically, this just means that this set thresholds function, I can only call this if I've already taken this lock ahead of time. So, you know, let's run this, and there we go. It looked like it worked. So, you know, let's add a lock equals true, and let's fix this. You know, let's not fix this right now. I'm just thinking about how I might want to deal with this. We'll come back to this later. So, you know, again, these are issues you're going to run into as you port devices over. Like if you're locking things, you have to worry about deadlock and you know, what owns taking that lock. I'd like to hide all that lock logic from the user of this class, but I might need to pull this lock logic out so that the MPR121 class user has to take that lock, so that then they can start calling all the functions. I don't want to get into that in this stream. I've only got about 15 minutes before I have a hard exit that I have to make anyways. So, okay, so let's see what's next then. So I've set my thresholds, and now our baseline filtering registers. So I want to set these values. So let's go back to our reset and let's put these in. And this looks like this should be a really easy, quick little port. And I think that, okay, yeah, it looks like all my spacing is correct there. Okay, so this, I just need to write all of these register values. So it's literally, I can just replace a lot of this stuff. So let's just take this and just take all of that and replace it with that, and then skip to the end and clean it up like that. That looks like it's correct for this. So yep, okay, so that's going to write all of these register values out. So let's save that, and just to make sure it works, let's run it. Yep, nothing exploded there, so that seems good. And then let's set these other configurations and enable the electrodes. So I want to port this over next. So let's do this, and this is going to be, again, really similar. I'm just writing out these register values, so I should just be able to find and replace all of these things. Oh boy, did not mean to copy and paste that. So let's, I had the wrong thing in the buffer there. Okay, let's replace these again. Do that, and then I'm gonna have to go through and manually terminate the byte strings here, or the byte arrays rather. Okay, so we'll do that, do that. Okay, so we saved that. Now let's run this, and nothing exploded. Okay, so at this point in theory our device is initialized. So let's finish porting over. Basically there's a touched function, and if I call touched or is touched, then I want to check and see, I can basically check which of the pins have been touched which ones it detects, and it's just reading a register right here we can see. And so I just want to check real quick though. I'm going to look at the example code because I want to make sure that it's really just only those couple functions that I need to port over. So basically, yeah, it's just calling touched, and it just goes through and checks to see which pins were touched, and basically a bit will be flipped on and off for each of the pins. So yeah, it looks like it's just the touched function that I need to port over. Oops. So let's do that. Let's go and grab the code for that touched function, and let's port that over. So it's this function right here, and let's add that. And again, I'm going to remove the comment just because it's got a bunch of memory that it takes. Okay, so now I need to read a 16-bit register in this case. So okay, so this is kind of similar to what I did right here, but basically I need to change the size of the byte array that I read right here. So let's put this code below here first to start. Okay, so first I need to write out the register, the touch status register. And again, make sure I need to send that stop bit equals false because I'm going to continue by reading some data now. And so now I'm going to read 2 bytes of response data instead of 1. And so this result array is going to have 2 values. And then I'm going to turn this into a 16-bit value. So basically the way I'm going to do that is I'm going to return the results, and I believe, I can't remember if this is little endian or big endian values. Little endian means that basically your, let me see if I remember this correctly from memory, your most significant byte is last, I believe that's, let's look it up with Wikipedia. I always forget little endian versus big endian. And the Wikipedia page is the worst in the world because it should literally just be like the very first thing, that there should be a table up here that says little endian, big endian. You've got to read this paragraph here, and in the middle of the paragraph, here we go. So when storing a word in big endian, the most significant byte, which contains the most significant bits, is stored first. Okay, so if it's big endian, then the very first, so result 0 will have the high 8 bits of this 16-bit value, and then result 1 will have the low 8 bits of that value. And actually, if I go back to my Python code, I make this really explicit. So it's this read U16LE means read an unsigned 16-bit little endian value. So I know it's little endian, and then that's, if I go back to Wikipedia here to double check, so little endian reverses that format. Again, I would just someone put a table on here, please. It's just little endian, here's an example, big endian, here's, if I have to read a paragraph, this every time, and you would think that I would learn this by now, but I haven't yet. Anyways, little endian, so reverses that. So the least significant byte is the first location. So my low 8 bits are first, and my high 8 bits are second. And this is important because I need to reconstruct this 16-bit value. So my low 8 bits, so my high 8 bits are the second value. So result 1 is my high 8 bits. So if I take that and shift it by 8 bits, and then if I OR that with my first byte, so that's my most significant, my least significant bits, which again, I'm just going to check. So yeah, the least significant byte is first. So basically the first byte I get back from the chip is my low 8 bits. The second byte is my high 8 bits that I store right here, like that. So okay, so let's save that. And then let's just have it, just get the touch value. Let's say MPR121.touched. And let's just have it print out the touched value that it gets. So, okay, let's have it run this and let's see what happens. So, okay, duh, there's, I left the old code in right here, so that's obviously not going to work. So let's remove that. And I guess just to be nice, yeah, I'll AND all of this by OXFFFF. This just makes sure that I get back a 16-bit unsigned value. I've gone through this before. If you don't do this, Python might get confused and think that this is a signed value. So I'm telling you, just ignore everything, and I'm just returning a 16-bit unsigned value in this case. So, okay, let's do that. And so, okay, so I get a value 0. Now, if I touch this with my fingers, let's see what happens if I get a different value back. So, I get a value 0 again. Oh, that's not very good. So, okay, well, let's start debugging this a little bit and see what's going on. Let's print out my result buffer, my result values that I get back here. So let's save that. Because I can tell this chip is detecting when a finger touches this. You see that red turns on. And if I remember correctly, that's the way that this chip works. Although it's not going off now, which is interesting. I don't know. Let's run this again and see what happens. But let's just print out that raw byte values that I get back. Okay, so I got a value 0, 0 back. Now if I touch this, I think what's happening is I initialized the chip, and then it probably initialized to the default state with my fingers touched there. Again, kind of like I ran into with the Circuit Playground at the beginning of this. So let's make this a little bit different. Let's put a loop inside of here. I'm just trying to think through how I want to do this while using this ampy command. Yeah, let's just put a loop in here. Let's do, let's import time. Oops, import time. Okay, so let's put a loop in here and let's do while true. Let's say touched equals MPR121.touched. Let's print out the touched value, and then let's sleep for 1/4 of a second. So just every 1/4 second, it's going to be printing out the values. Okay, so I'm going to do that, and now when I run this, I need to add the -n command so that it knows not to wait. Okay, so now if I open up the serial terminal, I should see every 1/4 second the output of this, and I don't. So let's try this again. I must have gotten something wrong in my code, so I'm going to run this without -n, and this just means if something fails, if I get an exception. Okay, yeah, so here we go. Oh, interesting. No I2C device at address OX5A. Interesting. Maybe I tweaked a connection there. Let's try this again and see if we get something back. Okay, I must have moved a wire there on accident because it's running now. So let's run this again with -n and see now. Now I should hopefully see when I open the screen. There we go. So there's my 0 value. Now when I touch this, hey, okay, so things are changing. So, I'm touching less of these, and you can see when I touch nothing, I get 0 values. When I touch things, I start to get values. And basically the bits of this 16-bit value will tell me which pins have been touched. So real fast, because I literally have a few minutes before I have to leave. I've got to run to something in a second here. Let's add this isTouched function, which just helps me figure out, I can pass this a pin and it will tell me is that pin touched or not. So let's add this, and I don't need that print there anymore. Let's add this, and oops. So, okay, let's delete that comment. And so again, this is just going to go, it's going to call the touched function, then it's going to check and see is that bit for the pin that I specified set or not. So there's no conversion here. This is valid Python code. This is also valid MicroPython code. So let's save that. And now let's change my loop, and let's say if MPR121.isTouched, and let's say pin number 0. It's all the way on the far right, so we'll say 0, and print pin 0 touched. So okay, so I'll save that, and then let's quit out of here, and let's run our script again. Now hopefully this didn't error out, but let's I'm just gonna fly blind here. Now if I touch this, hey, check that out. It notices pin 0 touched, and then I take my finger away and I touch it, pin 0 touched. And it is pretty, like I can touch over here, it's not detecting pin 0, but when I touch right here, pin 0 detected there. So cool, so I'm gonna wrap this up then. This is a basic, very fast and dirty port of the MPR121 capacitive touch sensor. I'll put this file up on GitHub Gist so that you can grab this, and this is an example of the usage, and you could put your main program in here, or if you save this as MPR121.py, you can just import MPR121 and then start using this MPR121 class. And so here's like a little example of its usage. So if you want to get started and use it, but I'll do a proper library next week for this and do a little guide and probably a video on it also. But I just wanted to show in this video, like I said, I started with, for the Circuit Playground Express boards, the boards that have the SAMD21 and the extra flash memory, they have native capacitive touch sensing built in, and we'll have that available, and it's really easy to use with like a simple little function call. And then for the boards that don't have that, so like the M0 boards you can buy today that don't have that extra flash memory, or this would work on the ESP8266 also, you can use a chip like the MPR121 capacitive touch sensing module, and you can see it's pretty straightforward. Now, you don't have to create this driver every time you want to use this. If you just want to use this board, download the driver that I'm going to publish from this. But hopefully you saw kind of my thought process of how I convert from an older Raspberry Pi driver into a newer CircuitPython driver for this. So hopefully maybe you learned a little bit from this. Give you some tips if you're working on doing some driver porting yourselves for this. So, okay, I really have to go. I've got to leave here in a minute here. So I'm going to end this stream. Let's see, I'll jump back here. If folks have questions, maybe throw them into the chat real fast. But I don't see any questions. Yeah, someone was mentioning about locking, and so yeah, like I mentioned, I need to come back and look at our I2C module, because yeah, I got a fun little deadlock there. It's not threads that are waiting. It's just there's a mutex on this resource, and so it's I'm doing things in a way where I've got two things that are trying to take that mutex, and it's they're both waiting for each other effectively, which that is the classic deadlock problem. So good way to learn computer science basics, by making all the mistakes that you learn about in school. Anyways, I'll wrap up the stream, so thanks a lot for watching. Check out twitch.tv/Adafruit. That's where I stream this live. Usually every Friday I do a live stream. And check out youtube.com/Adafruit. That's where this video will be up, and all kinds of other fun project videos. We've done tons of cool videos on CircuitPython and MicroPython. I don't think we're going to stop anytime soon, so keep your eyes peeled for more great content. And if you like this, if you find this useful, then click the like or the comment or the subscribe button. Let us know that this is good content, and we'll keep doing all kinds of stuff like this. So I've got to run, and it looks like I've tired my cat out. Capacitive touch sensing is obviously not the most interesting subject for cats. So until next time, this is Tony from Adafruit. So thanks for watching. I'll see you later.